Today is very simple. We don't have many requirements for today's session, just the Smart Citizen kit in different variants that you have with GPS, with temperature probes, and so on, or the basic kit. And we're going to talk about air sensors. So air sensors basically is everything related to weather and air pollution parameters. The basic kit already does some of that, and as you know, we can expand the kit with different other sensors and probes. Basic kit measures air temperature and relative humidity, which are both directly related, barometric pressure, light intensity, particulate matter, noise, and total volatile organic compounds. We will see what each of these is, and what different considerations we have to take into account. Starting with temperature and humidity. As you know, well, temperature, there's nothing very complex about it. It's just simply how hot or cold, in this case, air is. In the previous session, we were talking about water. And as an additional measure or metric, we have as well relative humidity, which is the ratio of how much water vapor is in the air at the moment and how much it can potentially contain at a certain temperature. So it is relative humidity is directly related to air temperature. The higher the temperature, the lower the relative humidity, because it can hold less humidity. And that is, of course, directly related to the appearance of dew or moist on objects. We measure both of them with one sensor, one single sensor that is located in the urban board, as you can see here on the top right. So it's a very small sensor, which we call, well, it's a digital thermometer, but in what we call a MEMS, M-E-M package, which means that a very small, probably 2 by 2 millimeter black box is able to measure temperature and humidity. And then for some of you, we also have, you also have requested external temperature probes for measuring more accurately, which is this little probe that you see in the picture right here. Both sensors are exactly the same. So the probe contains something very similar to that other sensor in the urban board. However, the package is different. And this is very important because the urban board, of course, is contained in the enclosure. The sensor is affected by the electronics heat and the thermal inertia that the enclosure and the device gets over time. So obviously, it's going to be a little bit more affected by all of that than this external temperature probe. So if you need very exact measurements, we would recommend to go for this probe, and as some of you have already requested. Otherwise, this one is good. Limitations for the top one is that, of course, it's going to have less temporal representation or representativity. It's going to be a little bit smoother because it has the inertia of the enclosure and it's not going to be so reactive. And in terms of accuracy, of course, we have tried to calibrate the device in the different scenarios, but the operation modes of the device also affect the temperature readings, meaning if we are charging the battery or if we are posting data online versus storing it on the SD card, these temperature readings will be affected because the electronics will be generating more or less heat. And of course, the sensor will read that. Of course, it's our job to calibrate for that. And we have performed calibration in all the different scenarios, but no calibration is perfect. And of course, you have to assume that there's probably a little bit more error or offset of these readings versus an external temperature probe. None of the sensors need more calibration than that. If you want to recalibrate on your scenario, you can do so, but the external temperature probe should need no calibration, especially if it's located away from the enclosure and not on the enclosure itself, touching the sense, let's say the other parts. That's why we placed it in that position, and you'll see that it's connected to the enclosure by a plastic hook, or like a small hook or clamp to the device, to the enclosure itself, away from it, roughly at 3 or 4 centimeters, which we consider that the enclosure already doesn't affect. But if you want to put the sensor farther away, just so you know, there's a lot of cable inside of the enclosure that you can basically take out and take the probe and put it somewhere else, wherever you consider that is more relevant for your experiments. So don't think that the probe is there and it cannot move. There's plenty of cable inside of the enclosure, and you can just place it somewhere else in case that you think that is not placed in a proper spot. We also think that that place is convenient, or it is good because the sensor will not be affected by sun radiation, especially if you have shadows or other buildings that are, for instance, covering the sensors. This will affect the temperature readings for sure, and you will see that the sun radiation will hit up the enclosure and the temperature probe itself. So if you don't want the sun to affect it, you can even place it inside of a Stevenson enclosure or similar, and you can place it in any other spot with plenty of cable to move it around. Okay, in terms of another sensor, we have a pressure sensor that can basically measure barometric pressure or absolute pressure. Of course, needless to say, that the use of pressure is very important in how air currents move and weather. And the important thing is that with temperature and relative humidity, you can also have absolute humidity, which is the absolute content of water that you have in the air. The sensor, it's only placed in this case on the urban sensor board, is right below the temperature and humidity. It performs quite well in a very long or wide range from 50 to 110 kilopascals, and it also can give you above sea level height, so down to, I believe, one meter precision. So you can even use to determine at which height you are located inside a building or other things. The sensor doesn't need, in this particular case, no calibration or drift, and it doesn't get affected by any of the other sensors or the electronics buildup. Electronics buildup is simply okay to go. Other metric, so the microphone or the noise readings. This always raises a lot of questions, so I'm going to spend a little bit more time talking about this one. Basically, what we measure is the root mean square, or RMS, of sound pressure levels that are in the air. And we express that in dB, so in decibels, and that's probably everyone knows this, but decibels is not a unit. It's just a way for expressing a relationship of numbers, and it's widely used in acoustics and things like this. So some of the questions is that, what do we actually measure? Are we monitoring people, and are we listening to conversations and things like this? Well, in principle, no. So basically, we get the samples at high speed at 44.1 kilohertz, which means we are collecting samples at double the maximum hearing frequency of humans. We humans can hear more or less up to 22 kilohertz. So we sample at double data speed so that we are able to capture all the frequencies. But because of the limitations and also because of our principles, we only capture 23 milliseconds of noise samples each time, meaning that we capture 512 samples, which is at that speed 23 milliseconds. We preprocess them, meaning we apply a little bit of cleaning, and then we perform a fast Fourier transform, isolating 256 different frequencies, and we get a frequency spectrum, which we then correct by equalizing it, normalizing it, and then adapt to the human hearing capacities. This means that the microphone levels are already corrected, are already calibrated or equalized, and then also we provide levels these decibels that we provide them corrected to what it's called A weighting or A scale or C scale, which is the way that microphones should be corrected for representing better how the human hearing actually works and how humans actually capture each of the frequencies that get to each one's ears. So basically, after all that, we apply this correction only to represent better how we perceive those frequencies. We also provide the raw readings without correction if necessary. And out of those, that final frequency spectrum, we calculate the root mean square. So basically, we calculate the this value, which is roughly the roughly 0.71, the amplitude of the effective signal that we are capturing. So after that, we do not perform any other correction, and just to be clear, the only data that we collect is 23 milliseconds worth of sampling, which is of course not listening to anyone's conversations, and we also perform the FFT. All this data is available as well if you want to analyze it, and there's some examples on how to collect that data in the documentation. And important things to consider about all of this is that the microphone, as you can see here, is in the urban board. So basically, it's a microphone like any other one that has basically a small inlet for the sound pressure to go to the sensing element, but it's not isolated in any way from humidity, dust, or particles. So it means that if you place them on environments that have very high humidity levels, or you block it in any way with dust or any other thing, it could end up giving absurdly high readings. And we have seen this in many experiments. The sensor basically clips us at 99 decibels, and because there's something blocking the airway base or the sensing element, and it cannot provide any accurate reading. It can be recovered after a while if you leave it in an indoor environment in dry conditions, and probably after some days it can come back, but it's not certain that it will. The sensor is also calibrated in an anechoic chamber. So we perform tests to calibrate the microphone and the frequency response of the whole system. But obviously, sound is a very tricky thing to measure. And since the sensor is a low-cost one and is not located inside a professional microphone, certain frequencies can resonate in both the electronics board. So basically, we can make the electronics board vibrate, and the same with enclosure. So the enclosure can act like a resonator and generate other frequencies or amplify some frequencies that we're capturing, which means that even if the sensor is calibrated, it is not considered a class 1 or class 2 microphone. even if we aimed for a class 2 microphone, we didn't calibrate it in each of the different scenarios. And of course, it will have its limitations. Having said that, if you want to read further into this, there's more details also in the documentation, and there's a deliverable for previous projects, one of them called IceCape. In one of those deliverables, we explain extensively how the microphone was characterized and all the performance and improvements that we try to achieve.